If you book a trip on Amtrak today, the customer-facing interface projects seamless cloud computing. But underneath that polished app, the digital ticketing process glitches back to an architecture that predates the public internet. The back-end data ecosystem routes through a legacy system called Arrow, an automated reservation and ticketing platform launched in 1981. It was built directly onto physical mainframe hardware, designed to handle the heavy, continuous workloads of early airline reservations and global banks. To process these transactions, Arrow relies on IBM's ZTPF operating system, with core applications written in low-level macro assembler and C. Standard software migration tools fail in this environment. 4 decades of transportation business rules, automated pricing mechanisms, and passenger manifest logic are hard-coded directly into that assembler code. Modernizing a national railroad requires treating the legacy core as an infrastructure extraction problem rather than a standard software migration. Mapping exactly how deeply this code is tethered to the physical railway is the only way to upgrade a multi-billion-dollar network without causing a nationwide stoppage. Moving passenger data requires one set of protocols. Moving physical locomotives through congested routes like the Northeast Corridor requires entirely different infrastructure. The tangible logistics of the network are managed by CETC, Consolidated Electrification and Train Control. This flowchart maps the Amtrak CETC architecture. At the orange top tier, field equipment generates raw, continuous data. That data flows into the blue control centers tier, handling real-time train dispatching and power grids. Finally, the bottom gray tier executes physical commands, enforcing safety. In a physical rail network, data latency equates to train stoppage. If a dispatch query drops, the trains cannot safely proceed. Consequently, any downtime in this overarching architecture directly threatens the physical safety and minute-by-minute operational survival of the railroad. Insulated from those physical tracks is the data layer, handling the passenger information streams, reservations, and financial accounting. This flowchart details the full stack of that legacy data layer. At the foundation is the central green block representing the IBM mainframe ZTPF operating system. This specific architecture survives today because it was engineered for pure speed and atomic transaction processing. When thousands of users attempt to book travel simultaneously, the system executes actions like locking specific seats across a nationwide network in fractions of a second to prevent double sales. Over the past 30 years, rather than rebuilding this battle-tested data core, engineers continually built external enterprise layers around it. External channels like SAP, Oracle for Finance, and modern mobile apps were programmed to reach deep into the 1980s mainframe and pull their raw data outward. This created a dense, glowing central node wrapped by dozens of modern applications, tethered tightly to the original data streams. Piling new software onto an old foundation creates a structural dependency trap. Extract the core, and you break the tethers connecting every modern layer. The modern systems rely so heavily on the legacy inputs that the central core becomes impossible to simply remove. Amtrak attempted to escape this architecture in 2009 with RES-NG, a $74 million fully funded project explicitly designed to shut Arrow down. The effort collapsed. Nearly half of the planned software modules were never finished. The project stalled because ripping out the mainframe threatened the operational survival of the network. This presents a specific executive dilemma. You must replace the aging software, but you cannot cause an immediate disruption to operations. There are 3 potential pathways. Path 1 is a lift and shift migration. Path 2 is a complete replacement. Path 3 is a hybrid strategy. Path 1 leaves the technical debt completely intact. Path 2 introduces the exact operational risk that doomed the RES-NG project. The hybrid strategy begins with lift and shift. The Arrow engine moves to modern cloud infrastructure, preserving proven business logic without disrupting schedules. Phase 3 expands the architecture. New cloud-native applications and AI services are built in parallel alongside the legacy block. Finally, legacy components are gradually retired, dissolving only after their functionality is thoroughly validated by the modern replacements taking over. In a mission-critical environment, simultaneous parallel operation provides the engineering safety margin required to mitigate the risk of total system failure. With the legacy dependencies finally untangled, the railroad gains the ability to safely deploy cognitive technologies. The stabilized core can now communicate cleanly via APIs to 3 distinct new cloud modules. The first is the AI pricing module, which continuously ingests variables like weather, local events, and competitor availability. Instead of relying on the rigid low-fare finders programmed in the 1980s, this dynamic yield optimization automatically adjusts to changing demand. The second is the digital twin node, maintaining a real-time virtual replica of the entire Northeast corridor. Operators can simulate physical conflicts and evaluate alternative routing scenarios instantly, resolving bottlenecks before passengers are affected. The third is the Vision AI node, where trackside inspection cameras and hardware sensors feed visual data directly into predictive algorithms. This shifts maintenance from scheduled reactions to proactive, condition-based interventions based on actual equipment wear. As international rail systems have demonstrated, success requires balancing technological innovation with strict operational stability. Modernization succeeds by protecting decades of operational knowledge while building the parallel systems that will eventually define the cognitive future.